Swayam Prabha. Digital India. Educated India.
Hello, welcome to lecture 39. Today we will be discussing about buckling of columns with different boundary conditions. In the last lectures on buckling, we have mostly dealt with columns with pin end condition or pin boundary condition. In this lecture, we will see how to find the critical buckling load of columns with different boundary conditions. So, let me take the example of a fixed free column, fixed free but perfect column. Perfect column. So, we are trying to find out the critical buckling load. So, therefore, we have to apply Euler theory of buckling, and therefore, we need to take a perfect column. So, let this be the fixed free perfect column, let L be the length of the column. Let me draw the axis. So, this is the z axis, the lengthwise axis is the z axis, and this is the y axis, whereas this is the x axis. Now, here I have z equals to 0 and here I have z equals to L. Now, once so if I have such a column under axial buckling, axial compressive load P, so on this column an axial buckling load P is acting. Now, if we can all imagine that if such an axial compressive load P acts on the column and if P is greater than or equal to pre-critical, then it is going to get deformed or buckled as has been shown in this configuration. So, this is the deformed or buckled configuration. So, this is the actual column and this is the buckled configuration. Now, we will try to find out the critical buckling load for this column with a fixed free boundary condition. So, for that let me take a small elemental portion of the column, of the buckled column, and let me try to draw the free body diagram of it. So, let me take a small portion of the column. Okay, and so let this length be elemental, that is dz. This is the z axis and this is the y axis. Now, if this is an elemental portion of the buckled column dz, then let us see what are the forces that are acting on the column. So, one force is of course the axial compressive load P, and then we have a P, and next there are going to be two moment. So, let me call this as M, this is P, and let me call this, therefore, is going to be M plus dm by dz into dz. So, so this is the moment that we have. So, apart from the moment, there would be a shear force, which let me represent by the term Q. So, if it is Q here, I will have an opposite force, which is Q plus dQ by dz into dz. So, Q is nothing but the shear force. Now, so these are the forces. So, I have actually, so this is the free body diagram of the elemental column. Now, so these are the forces and moments acting on it. Let us also consider that there is an externally applied moment, applied force in the transverse direction, which, or in the y direction, that is the transverse direction, which we are going to say Q per unit length. This Q can be a function of z. Now, let us say that at any point let Vz be the transverse deformation. So, therefore, Vz is the transverse deformation, as in the case of previous lectures. Now, if this is the free body diagram, let us now at any, so transfer deformation at any arbitrary point z. Now, if this is the free body diagram, let us write down the force balance equation in y direction. If we write down the force balance equation in the y direction, so it is going to be Q plus and that has to be equal to 0 for equilibrium in the y direction. Now, if we simplify this, this is going to be dQ by dz plus small q, which is the applied transverse force, and that is equal to 0. So, let me call this as equation 1. Now, let us try to write down the moment balance equation. So, let me write down So, if we write down the moment balance equation, then we are going to have m plus dm by dz into dz minus m, that is the moment, plus we are going to have q plus dq by dz into dz into dz. So, we are taking moment about this point. So, about this point we are taking the moment. So, therefore, so that then we are going to have P into, so we are going to have P into dV by dz into dz. So, the total moment is actually going to be the difference of Vz, which is dV. So, we write this as dV by dz into dz plus the moment because of the external force, which is q into dz into dz by 2. Now, that has to be equal to 0. Now, let us simplify this. So, if we simplify this, we will see that all the terms that are associated with the square of dz can be neglected, because dz is a small parameter and square of that is even smaller. So, we can actually neglect that. So, we can neglect this because it will have a dz square. So, this can be neglected, plus this has a dz term. So, dz square term. So, this can also be neglected. Now, if we neglect these two terms and do further simplification, we are going to have dm by dz plus q plus p dv by dz, and that is equal to 0. Let me call this as equation 2. Now, if I see from this equation that dq by dz can be written in terms of q. So, dq by dz can be written as minus q. So, now let me try to substitute equation 1 into equation 2, but in order to do that I have to take a derivative of equation 2 with respect to z. So, if I take a derivative of equation 2, I am going to get this as d2m by dz square plus dq by dz plus p d2v by dz square, and that is equal to 0. Right. Now, what is this dq by dz? So, dq by dz is going to be minus q. Now, my q is in turn equals to 0. So, therefore, we have considered there is no externally applied force on the column. So, q equals to 0 as there is no externally applied force. Is no external force in y direction. Okay. So, if this is the case, then this del q by del z goes to 0. If that happens, then our equation simplifies further and becomes d2m by dz square plus p into d2v by dz square, and that is equal to 0. So, this is the third equation. Now, in this equation, we have also used this previously, that the moment m can be written as EI into d2v by dz square, because v is the transverse deformation or displacement. Now, if that is the case, we can write this as d2 by dz square into EI into d2v by dz square plus p d2v by dz square, and that is equal to 0. Right. So, this is going to be the case. So, therefore, for uniform cross section column, this can be written as EI d4v by dz4 plus p into d2v by dz square, and that is equal to 0. So, therefore, this is the final governing equation for buckling for any arbitrary end condition. So, for pin column this was a second order equation, whereas here it becomes a fourth order equation. It was a second order equation in case of a pin column because there was no shear force associated in a pin column, whereas here there would be a shear force associated. So, we will get a fourth order equation. So, this is the governing differential equation for buckling of column, uniform cross section column. Now, you must have noticed that while deriving this equation, we have not used any boundary condition. So, this equation therefore can be applied with for columns with any boundary condition. It can be fixed, it can be fixed free, it can also be pin, it can also be fixed pin. So, we can also use a pin boundary condition. Only that for pin we do not need this fourth order equation, second order equation is fine enough. Now, so this equation, let me call this as equation 4. Now, this equation can further be written as d4v by dz4 plus p by ei into d2v by dz square, and that is equal to 0. So, let this be called as mu square as in previous case. Therefore, this equation can be written as d4v by dz4 plus mu square d2v by dz square is equal to 0. Now, this is the equation where let me write it down, that nu square is nothing but p by ei. Now, we need to solve this equation. So, this equation is again a homogeneous fourth order differential equation, ordinary differential equation, which is very easy to solve. So, the generalized, so let me call this as equation 5. Therefore, the generalized solution of equation 5 can be written as Vz, which is A plus Bz plus C cos mu z plus D sin mu z. I am not getting into the intermediate steps of how to derive the generalized solution, but this is very straightforward because we just have a fourth order ODE and solving that is pretty straightforward. So, let me call this as equation 6. Now, A, B, C, D are constants which can be found out from the boundary conditions. So, what are the boundary conditions for a fixed column? So, let us see what are the boundary conditions for a fixed free column. So, the boundary conditions are at the fixed end, that is at z equals to 0, the displacement is going to be 0. So, V0 is equal to 0 and the slope also has to be equal to 0. So, dV by dz at z equals to 0 has to be equal to 0. So, what are the set of boundary condition at the free end? So, at the free end, that is z equals to L, the free end is free from any moment. So, we can say that the moment is equal to 0. So, what does the moment equal to 0 implies? The moment in turn can be written as E I d2v by dz square is equal to 0, which in turn says that d2v by dz square at z equals to L has to be equal to 0. Now, what is the other condition? That the shear force Q has to be equal to 0. Now, how do I write that the shear force is equal to 0? So, the shear force Q is basically minus dm by dz minus p dv by dz. So, this is coming from equation 2. So, from equation 2 we can see that Q is equal to minus. So, from here we can see Q is minus dm by dz and minus p dv by dz. So, we are using that expression and we are saying that Q is equal to 0, this and that is equal to 0 at z equals to L. So, these are the 4 conditions that I have. So, this is the condition 1, this is the condition 2 and this is the. So, this further can be written in terms of V as E I d3v by dz cube minus p d2 dv by dz, that is equal to 0, which can further be written as d3v by dz cube plus mu square, because we get a p by E I dv by dz is at z equal to L is equal to 0. So, this is the fourth equation that we are going to have. Now, let us substitute this condition on the generalized equation and see what are the values of A, B, C and D. So, let us first start with condition 1, that is V0 is equal to 0. So, what do we get? If we put V0 equals to 0, we get A. So, Vz, let me write it down just for ready reference, that Vz is A plus Bz plus C cos mu z plus D sin mu z. Just let us keep this handy so that we can refer to this as and when required. So, therefore, V equals 0 equals to 0 is going to give me A plus C equals to 0. So, let me call this as equation A. Now, let us substitute that dV by dz at z equals to 0 is equal to 0. What does that give? That gives that A is anyhow gone, B, and we have B plus mu D. So, we have, this is going to imply that B plus mu D is going to be equal to 0. So, let me call this as equation B. Now, let us use the third condition, that is d2v by dz square at z equals to L is going to be 0. So, if I take d2v by dz square, I am going to get minus mu square C cos mu L minus mu square d sin mu L is equal to 0, which can be further simplified and written as C cos mu L plus d sin mu L is equal to 0. So, this let me call as equation C. Now, let us come to the next equation, which is coming from shear force equals to 0, which is d3v by dz cube plus nu square dv by dz at z equals to L is equal to 0. Now, what is d3v by dz cube? d3v by dz cube is going to be minus, so plus, you have nu cube C sin nu L plus minus nu cube d cos nu L. This is coming from d3v by dz cube plus nu square is going to be b minus nu c cos nu L minus nu d sin nu del L, and that has to be equal to 0. Now, if I try to simplify this, let us look into this. So let us if we look into this, sorry, this is going to be, so dv by dz. So, this is going to be sin mu L and this is going to be cos mu L. Now, if we look into this, then this is going to get cancelled out with this, and this is going to get cancelled out with this. So this is going to get cancelled. So, we have made some mistake in the calculation of sine. So, we are going to have this as minus nu. So, this is going to be nu square b minus nu c. So, this is plus. So, this is plus. So, this is going to get cancelled out. So, we will be left with only mu square b is equal to 0, which implies that b is equal to 0. Now, if b is equal to 0, let me call this as equation D. Now, therefore, we can summarize this and write this as b is equal to 0. If b is equal to 0, from equation B we get d equals to 0. Now, and the other thing we get is a equals to minus c, and from equation C we get c cos mu L is equal to 0. Now, if c cos mu L is equal to 0, c cannot be equal to 0 for non-trivial solution, because if c is equal to 0, the entire thing is going to be 0. So, it is non-trivial. So, cos mu L therefore has to be equal to 0. Now, mu L is going to be 0 if it is 2n minus 1 pi by 2. Therefore, mu has to be 2n minus 1 pi by 2 L. So, therefore, we get this net solution. Okay. So, Vz is going to be a 1 minus cos mu z. So, this is the solution that we have. I am going to summarize this, and we are going to talk about this in more detail in the next lecture. Thank you.